Hi class, today we're learning about modeling with trigonometric functions. So modeling again just means we're given a realistic situation, something in the real world, and we're using math to answer questions about it. We're making equations, we're making graphs, it's all kinds of fun. So that's what we're doing today. So remember to come up with a trigonometric function, you need to find the axis, the amplitude, the period, and the phase shift, depending on whether you use sine or cos. Okay, so when we're reading the information, we're trying to find the axis, so that's the middle point of the curve, the amplitude, so the distance between the middle point and the max, and the middle point and the min, and also the period, how long it takes to complete one revolution. Okay, then we look at information about, does it start at a minimum, does it start at a maximum, or when do the minimum and maximum occur? And that information will help us determine whether we use sine or cos, whether we need to be a negative sine or cos, and if we use a phase shift or not. Okay, so just that's the type of information we're looking for, so I'm going to organize all my information in that way. So this first one is about tides. Tides are typically used for periodic functions because they repeat. So this one is just an example of New Brunswick. On one day in October, the tides have a high point. So again, that's a maximum of approximately 10 meters. Just getting my pen out. 10 meters, so that means that 10 meters is a maximum at 2 p.m. and a low point of about 1.2 meters at 8:15 p.m. So this particular sailboat has a draft of 2 meters, which means it can only move in water that is at least 2 meters deep. The captain plans to exit the harbor at 6:30 p.m. Can the captain safely exit the harbor in the sailboat at 6:30 is what that means. So really we have to think about what this is asking. So you have to say at 6:30, is the height greater than 2? So to do that, we need to come up with the equation and a graph and figure this all out. So we're going to use our information about a maximum and the minimum to help draw this, and then we're going to come up with some information. Okay, so I'm going to have each tick here represent, an o'clock. So this is going to be like noon. So this is 2, or 6, 8, 10, and 12. Okay, so this is the time, and then this would be the height at the given time. So I know that I had a minimum of 1.2 and a maximum of 10, so I'm just going to go up by ones. I'll even affirm. So there's 2, 3, 4, 5, 6, 7, 8, and 9, 10. Okay, so I have at 2 o'clock, I am at 10 meters. So I know that point for sure, and that's a maximum. And then at 6:30, so halfway, 6.5, I am at 1.2. So 1.2 there-ish. And I know that that's a minimum. So what happens after that, we can think about. So that means this kind of, you don't make it a line. But you can think about when the maximum would occur again. So between this and this is 2 to 6:30 is 4.5 hours. So in another 4.5 hours, so 11 o'clock, you would be back at a maximum again. Okay, you can kind of use that logic. Okay. Sorry, I made a mistake. You guys are all like, Mrs. Weems. The minimum occurs at 8:15. That's my bad. 8:15 is when it's at 1.2. There we go. Okay, so again, this kind of curves down. Okay, and then it will be going back up again. We don't know exactly how. And so that means here it will be sloping down. We don't know exactly where it hits, but probably somewhere like that. It would follow the same curve. So it's asking at 6:30. So at 6:30, is it above 2? So it looks to be that it is above 2, but we need to come up with the equation and find out for sure. So it looks like it will work. So let's come up with the equation now. Well, the first thing we want to identify is our max is 10 and our min is 1.2. So from there we can figure out the axis and the amplitude. So the axis is just the halfway point between those two. So it'll be equal to 10 plus 1.2 divided by 2, which in this case is 5.6. So therefore, the c value of the function will be 5.6. Okay, now we need to come up with our amplitude. The amplitude is just the distance from the maximum to the axis. So we could just do 10 minus 5.6, and that gives us 4.4. So therefore, our a value is going to be 4.4, or it might be negative 4.4, depending on what we choose. Okay, so that's what the max and the min tell us. Now we need to look at our period. Now this is a bit dicey, because you might say, well, we can't figure out the period because we only know max to min. But remember, max to min is half of a period. Okay, so we're given the time from the max to min is, it's from 8:15 to 2 o'clock. So that's 6.25 hours. Okay, it's not 6.15. Okay, it's 6.25 hours because it's 6 hours and 15 minutes, which is 6.25 hours. So therefore, the full period would go max to max again. So we would have to do 6.25 times 2, which is 13. Sorry, which is 12.5 hours. So our k value then is 2 pi divided by 12.5. So how we do that there then is we don't want a decimal in the denominator. So to get rid of that decimal, you have to multiply it by 2, right? And if you're multiplying the denominator by 2, you have to multiply the numerator by 2. So we get 4 pi over 25. That would be an exact fraction that would represent what we did there. So now let's take a look at if we want to use sine or cos. Well, we know where the maximum is. We don't know exactly where it hits the axis. So we want to use cos. Okay, so we're going to use cos because we know where it hits the maximum. But the time shift, we know that it hits the maximum at 2 o'clock, so our d value is going to be 2 because the maximum is shifted 2 to the right from where it originally is. So you have to think normally the maximum was here, and now it's been shifted 2 to the right. You don't think, what would I do to get it back to the original? You think, how was the original changed to get it to where it is now? So it's going to be 2 to the right. So therefore, our function is h at t. So you identify your variables. Let h at t represent height in meters at t in hours past noon. Okay, past noon. So h at t would be 4.4. We don't need to make it negative because it's starting at the max. Cos bracket 4 pi over 25. Bracket t minus 2, because you subtract d, plus 5.6. So that, in blue there, is our function. So now we just use it to solve the problem. We let t equal 6.5. I'm running out of room, so I'm going to just write it up here. Hopefully you have room on your sheet. So you let t be equal to 6.5, because that would be 630. And so you just find h at 6.5. You put it through the function, making sure you're in radians. And you get out 2.8 meters. So that is above 2, so then you can make the conclusion that yes, the boat can safely exit the harbor since the tide is above 2 meters. All right, so that is example 1. So again, we use the maximum and the minimum to come up with the axis and the amplitude. Then we use the period. We realized that we only were given information for half a period, so we doubled that to make it the full period. And then we decided to use cos because we knew where the maximum was, and it was just shifted 2 to the right from where cos maximum normally is, which is on the vertical axis. Okay, next question uses a table of values. So in this case, we kind of have to make some assumptions, which isn't always fun, but we do it anyway. So this is more realistic to the type of thing you'll be doing in the real world, using data and then coming up with a model that is close to modeling what's going on, but it won't be exact. So this shows the average monthly means of the daily temperature, okay? So this means that on January 15th, then the average monthly temperature was minus 4.8 degrees. So then 45, that's the 45th day of the year, not February 45, obviously, and so on and so forth. So this would be the 350th day. So they want us to plot the temperature. Okay, so day of the year is here. Actually, I'm going to call it T, just so we don't confuse it with the other B. So this is T for time, and this is capital T at little t, or temperature at time. Okay, so we need to get all the way up to 350 on this axis. So I went up by 25. So 25, 50, 75, 100, 150, 200, 250, 300, 350. Okay, and I noticed that my minimum temperature here is minus 4.8 and my maximum is 21.9. So I need to get up to that much information. So I went up by 5. So here is -5, -10, 5, 10, 15, 20. Oh, I'm going to have a lot of room, so I'm going to change that actually. I'm going to go up, do 5s. Every other one be 5 instead. So here's -5, 5, 10, 15, 20, 25. Okay, so now you actually just go and plot all these points. So I'll do it. I'm not going to really talk while I'm doing it. You can do the same thing. Just make sure you're being as accurate as you can. So, you know, this is 25 for one tick here, so 15 is just over halfway. And then, you know, you're just as accurate as you can be with your scale. So that's why choosing, here I said I wasn't going to talk and now I'm talking. That's why choosing a good scale is really important. Okay. Isn't this fun just watching me work? Okay. It's kind of nerve-wracking actually for me. Okay. So that's the best estimation that we have, okay, for this. Okay, so you can fit a sinusoidal curve to the data. So often people just put a straight line here, but think about it. If these two are the same, the minimum is probably somewhere halfway between them, right? If those are the same, then there's some, oh man, guys, you try to do this. I know you're making fun of me right now, but it's hard to do this on here. Okay, so it would have gone up somewhere here, and it would be going down, slightly down, and up, and just as many points as possible. It might not be perfectly through all the points. Okay, so there's a general sinusoidal curve. All right, so now we have to make some assumptions here. Okay, we're going to assume that there's a max, that the max is what's given to us, that the max is 21.9 degrees. Okay, is that true? I don't know, but we need to at least name that that's what we're assuming. And then we're going to assume that our min is 4.8. Okay, is that true? I don't know. It looks like it might have gone slightly below. So if you gave me some reasoning, like you put your min down to -5, you think it's dipping down to -5 or -5.2, that would be acceptable as well. I just want to see some reasoning there. Okay, but I'm just going to take our min number as -4.8. Okay, so from there we can come up with the axis. We just average them, 21.9 plus, sorry, not plus, minus 4.8 divided by 2. So that's 8.55. Okay, and our amplitude is again just 21.9 minus 8.55. So that is 13.35. Okay, so there's our A value and our C value. Okay, the period is 365 days because it's a full year. So therefore our K value is 2 pi over 365. Okay, and it asks us to come up with the sinusoidal curve. So it's best to use cosine here because we want to know when it first hits the maximum. Okay, and we already know that it hits the maximum when t is equal to 197. So that's what we're going to use. We're going to use cos because we know when it hits the max, and we're going to use then a d value of 197 because we know that's how far it's been shifted over and to hit the max. So now we just say let T at T represent the temperature in degrees Celsius at day T after, and then you could say like something like where T equals 1 represents January 1 or something like that. All right, so now we come up with our formula. T at T represents 13.35 cos bracket 2 pi over 365 bracket T minus 197 bracket plus 8.55. All right, so now you can actually use this function to answer part B, which is estimate the average daily temperature on the 200th day of the year. So again, I'm running out of room, but part B, you would just find T at 200 and then see how close it is. So it should be somewhere, obviously, between 21.9 and 20.7, but it might be slightly off because this is a curve that's our best estimation possible. It's not going to be exact. So I got 21.8. You can try that for yourself there. Okay, so now we move on to example 3, which has us see the difference between the population in owl size and mice. So basically, owls eat mice. So you can think about if there's lots of owls, then what happens? Okay, so there are lots of owls, they're eating lots of mice, so the mice get fewer in numbers, so there's less mice for the owls to eat, so the owls become less. Well, when the owls become less, the mice start living longer, and so the mice increase, but then the owls are like, oh, I can eat more, so they increase. So the population of predators and prey are both related to each other cyclically in periodic functions. So that's something that animal and conservation specialists can study, and you can often model their lifespans or their population, by sinusoidal functions because they're linked to each other. So when one goes up, the other goes down, etc. It's really actually quite interesting. So let's take a look at what's going on here for owls and mice. So the population size of owls can be modeled by this function. So what can we take from this function? Well, first of all, we can see that 1,000 is the axis, and then 100 is the amplitude. So our maximum amount of owls that we ever have is just at the axis 1,000 plus 100 when it's at its max to get up to our top. So 1,100 is the highest amount that we would ever have of owls. The minimum then would be minimum is at the axis, subtract the amplitude, so 900. So basically we're just cycling between 900 and 1,100 owls, with 1,000 obviously being the average. Now the K value is pi over 12t, so what does that mean? Well, K is pi over 12, so therefore we have pi over 12 equals 2 pi divided by the period. So we can use this to find the period. Okay, so the period is actually just equal to 2 pi divided by pi over 12, which is the same as multiplying it by 12 over pi, so 24 months. So 2 years is the period. So it's cycling between 1,100 and 900 every 24 months, which is 2 periods. So we can sketch this for 4 years. So T in months, and this is O at T, so the owls at that time. Okay, and we want to get up to 48 months because it asks for 4 years. So how can we do this here? How many do I have? 1, 2, 3, 4. 1, 2, 3, 4. So we want this to be 48. So this will be 24. And this will be 12. And this will be 36. Okay, so what's happening here? So I'm going to do a little break in the data and have us start here at 800. So this is 900, 1,000, and 1,100. Okay, what else do we know? We know that this is the sine curve. So it's going to start on its axis because it's a positive sine curve. So it's going to start at 1,000. And after 24 months, which is 1 full cycle, it'll be back on its axis. Okay? And then halfway between the beginning and the end, it will be again on its axis. Okay? So halfway in between this, and at 6 months, it will be at a maximum. And at this 6 months, it'll be at a minimum. Okay, that's the basic sine curve. So this is its pattern that it's completing in 1 cycle, which we found to be 24 months. So then that pattern will repeat again to go up to 4 years. So basically it does this. There it goes, cute little thing. All right. So now we can look at the population of mice. Now mice, we can see, man, there's a lot more of them. So its max is, I'll use a different color, is going to be at the 20,000, which is the axis, plus 4,000. So we're looking at 24,000 mice is at the max. And our min is just the axis, so 2,000, or 20,000, sorry, minus 4,000, so 16,000 mice is the minimum. Okay, so basically we're going between 16,000 and 24,000 mice. Okay, our period is the same logic as before. It's also a 24-month period. So now we just need to sketch this. Now you'll notice I gave more space here because we have more variability. I'll also go up by 6, so this is 12, 24, 36, 48. Okay, and we'll take a little break here. This is 16,000, 17, 18,000, 19, 20,000, 21, 22,000, 23, 24. So this is M at T in thousands. Okay, and this is the time. So notice, however, that this is a cos curve. So it starts off at its maximum of 24,000, which means after one full cycle of 24 months, it will be back at a maximum, which means halfway in between, it will be at a minimum of 16,000. So halfway in between here, then it will be at its axis and axis, okay? And that pattern repeats. So there we go. You'll notice the amplitude's a lot bigger because there's a lot more variability in the number of mice. So now they want us to compare the graphs and discuss the relationship between the two populations. So the best way I found to do this is to just label the different points. So like this is point A, this is point A, this is point B, this is point B. So you're going every 6 months. You're comparing basically what happens in every 6-month period, but it just helps our conversation to label them. And I use letters instead of numbers just so the numbers of the formulas aren't confused. Okay. So you can scroll down, and I'm gonna do more talking than I am writing. So for the first 6 months, so that's basically from A to B, the owls are increasing and the mice are decreasing. Okay, and then for the second 6 months, so B to C, as the mice decrease, the owls start decreasing, which makes sense because there's less mice, so there's less owls because there's less mice to be eating. And then for the third 6 months, so basically between C and D, you can see that as the owls decrease, they've decreased so much, the mice are saying, hey, we can start increasing because we're not getting eaten so much. Okay, and then between D and E, as the mice increase now, now there's more mice, so the owls can go back up again. Okay, and then this pattern keeps repeating. So now as the owls increase, the mice will decrease, and this keeps going on and on and on. Okay, part C asks to look at the ratio, the mice to owl ratio. So over time, we're going to look at 0 months, 6 months, 12 months, 18 months, and 24 months. What happens to the population? So at 0 months, the mice population is at 24,000 and the owl population is at 1,000. So that's a 24 to 1 ratio. Okay, at 6 months, the population of the mice is at 20,000 and the population of the owls is at 1.1 thousand, so 1,100. So this is an 18.2 to 1 ratio of mice to owls. At 12 months, we're at 16 and 1, so that's a 16 to 1 ratio. Okay, notice I'm always doing it in terms of to 1. So how many mice are there to 1 owl? That's what I'm doing here. So at 18 months, there's 20,000 mice and 0.9 thousand owls. So that is a 22.2 to 1 ratio. So there's 22.2 mice to every 1 owl. Then at 24 months, we have 24,000 there, 1 here, so it's a 24 to 1 ratio. Okay, so what does that mean? How does this change over time? Well, this is also going to be a sinusoidal function. This ratio is also sinusoidal. So the way in which the ratio changes is going to repeat every 24 months as well. Okay. When is there the most food per owl, and when is it safest for the mice? Well, this actually happens at the same time when the mice to owl ratio is the highest. Okay, so it's roughly when T is equal to 21 in the 24-month cycle. So if you go and take a look, it's when, sorry, I'm having trouble here. It's safest for the mice when there's the most food for each owl. So then there's the most mice for every owl. So you could say it's here at 24 months or at 0 months. Sorry, those are the times when it's safest for the owls. All right. Okay, so that kind of just gives you some understanding of how sinusoidal functions are used in the real world, the different type of things they can model. So temperature, population, and tides are very, very common examples that come up, as well as things like Ferris wheels and anything that's a physical circle going around and around. So hopefully this helped you in your understanding that you always need to find the amplitude and the axis and the k value using the period if you're given information. And if you're given the equation, you use the information to find the maximum and the minimum as well as the period. So thanks for watching, guys. I hope you learned lots.